Hi, my name is Nish Senapati, and over the past summer, I worked with Professor Jose Blanchett on solving a conditional value at risk constraint problem, like a chance constraint or optimization problem. Yes. So over this presentation, I'll first go over the background and motivation for my project. Then I will formulate the problem in mathematical terms, and then I'll start talking about the optimization algorithms that were developed during the summer. So for the formulation of the problems, I'm going to be looking at two different problems: the maximization problem and the salvage fund problem. And I'm going to talk about the optimization algorithms developed for both, along with the numerical results that came out of these experiments and algorithms. So many systems nowadays face optimization problems with probability constraints. So for instance, in a power network, you would want certain values to be minimized without the risk of, say, the power network failing. Or in autonomous vehicles, you want, say, like the distance or the amount of power that the engine is putting to be optimized without the probability of a crash occurring. So you want that to be extremely small. So like you can already see that there's a ton of fields where you can use these kinds of optimization problems with probability constraints. It's becoming like a more increasing field of research. So the way that you can formulate this problem is you can minimize a certain linear combination with respect to x of c transpose x, so that's just a dot product, subject to the probability that a certain risk factor, x with a random variable psi, subject to some certain risk factor, needs to be very low. So there's been significant research on finding solutions to these types of problems, which we're going to call chance constraint optimization problems. So one thing that you can do with this exact equation right here is you can actually reformulate it using something called the value at risk measure. The value at risk measure you can think of as the minimum point in a CDF such that the CDF up to that point is greater than a certain value. So for instance, like if you have a CDF and then you want like the 95th of a CVAR measure, you want the minimum point such that 95% of the CDF is covered. And what actually happens is this original chance constraint minimization problem can be shown to be equivalent to this one, where you say you're minimizing the same function, but now it's with respect to the value at risk of this risk factor being less than 0 for a certain 1 minus delta. So in this case, you originally had probability of the risk factor being less than delta. Now you're saying that the value at risk of 1 minus delta. So if you had if you didn't want to, if you want the probability to be less than 1%, you want the value at risk to be 99th percentile. Unfortunately, with both of these problems, it's actually been proven to be NP hard and intractable in most cases. Additionally, this VAR constraint has a lot of extra limitations, which make it very hard to use. So there's a risk measure, such as the VAR constraint or the original probabilistic constraint. You want some certain coherent factors into it. And the VAR constraint is actually not a coherent risk measure. It's missing a few things that would make sense logically for a risk measure. Also, typically, it's a non-convex function, which makes it very hard to optimize. Finally, the VAR constraint, if you think about the same example I've been talking about, the 95th percentile, it doesn't include anything that happens beyond the 95th percentile. It only includes that specific point, which seems a bit counterintuitive. You want to include all of these like heavy cases of probability failures. So these are all limitations to the VAR constraint, and for that reason, you have these limitations, so you introduce a new way of measuring the probabilistic constraint. And this way we call it the conditional value risk. So the conditional value risk, if you think of the VAR constraint as a point where the CDF is greater than 95% or 99%, the conditional value risk can be thought of as the expected value of all exceeding parts of the probability distribution. So the CVAR was introduced around in the late 1990s and has already been used in a lot of different aspects, such as portfolio management, the supply chain, and power system analysis. And a lot of the limitations that were mentioned in the VAR constraint, specifically the not coherent risk measure, is not non-convex and doesn't include scenarios, are all immediately solved by CVAR. It is a coherent measure. It is a convex function. You can prove this, and it does include, as you can see, like all the points beyond the value at risk original thing. It includes every single point, and it takes a weighted average of them at the expected value. So instead of this minimization problem, we can instead replace the VAR with a CVAR and approximate that problem using the CVAR optimization problem, which is shown here. So this is a convex approximation of the VAR problem, and since it has so many of the appealing features, it makes it a much more appealing alternative. So there are a few properties of CVAR that we have to quickly go through before we can move on to the problem formulation. So first off, the CVAR is a convex function, which is good because this minimization problem becomes much easier to handle. Secondly, you can define this function here, which is we call h of a certain alpha, to be z plus 1 minus alpha, the expected value, as exactly shown here. And you can show that if you minimize this function, this function minimization is actually equal to CVAR of alpha of x. It's also equal, the values that reach this minimum are the VAR, but we really care about the CVAR here. The fact that you can minimize this function with respect to z, and then you can get a CVAR of the original random variable that you're looking at. So how do we use this? So we originally had this optimization problem here. And so if you can take what we call a Lagrangian reformulation of this problem, where you add just in an extra, you add in the chance constraints with an extra lambda in front, then you can say we're trying to minimize the original function plus this constraint with respect to x. Now you have this new minimization problem, and here's where we can exactly apply this theorem. So the CVAR, you can say that if we replace the CVAR function that we are looking at with this theorem and use this h, you're minimizing with respect to x and z of this new function here, c transpose x plus lambda z plus lambda gamma to the 1/2 blah blah blah. And so now instead of minimizing with respect to one variable, you're minimizing with respect to two variables, and you're basically trying to find this problem will be if the Lagrangian relaxation holds, would be equivalent to the C-bar approximation optimization problem that's shown here in equation 3. Okay, so our goal is to solve this problem from equation number 5 here. So, and we actually, if you look at this part right here, there's a factor of gamma to the -1, and basically we wish to solve this problem efficiently as gamma goes to 0, which would make this entire term blow up, which is also equivalent to alpha going to 1, where you're going to be name changing between gamma and alpha. You just have to remember that gamma is equal to 1 minus alpha. And so we aim to solve this optimization problem efficiently, and as I'll discuss later, this actually equates to improving the efficiency of evaluating this expected value for different xi or random variables. In our case, we're going to be looking at heavy-tailed xi. So a heavy-tailed function, as it probably is obvious, has a heavy tail distribution, which means there's a lot more weight on its tail than usually like you see in comparison to like a normal distribution. And so if you have a lot of extra weight on these tails, a lot of these heavy extra parts of the random variable that normally would almost never happen start to happen a bit more often, which creates all of these risk factors, for example, being larger. And that's these heavy tail distributions are like they create more probability of a risk happening. So yeah, we need to improve the efficiency of such evaluations. Okay, so I'm going to discuss something. So we had this original problem in problem 5 as shown here. And we want to do these solve for x and z as gamma approaches 0 or alpha approaches 1. So these problems struggle from inefficiency mainly due to the fact that if you remember, z would be the c-bar of the function. So as gamma approaches 0, or as you want to make your probabilistic constraints more and more tight, your c-bar is going to become higher and higher. It's like, oh, I want to make my risk constraint 1%, 0.1%, 0.001%, etc. So as gamma approaches 0, x and z will approach infinity. So that's going to cause a lot of these inefficiencies if you want to solve for these things as they're going to higher and higher values. But what you can notice is that for a heavy tail distribution, you can apply two transformations. You can say x is equal to x bar over a certain factor, gamma to the 1 over a, where a is the scale parameter of the heavy tail distribution. And you can also say z is equal to z bar over gamma to the 1 over a. So, and then you can, once you apply these two transformations, you can minimize with respect to x bar and z bar. So this is more of an intuitive transformation rather than one that just immediately makes sense. You're basically saying as gamma goes to 0, you have these two values which approach infinity, and we guess that both of these values are of the order of gamma to the negative 1 over a. So when you apply these transformations, you're trying to get rid of this increasing bound as gamma goes to 0. So it eases the divergence rate of x and z, and thus when you solve for x bar and z bar, you won't have these same problems of approaching infinity because you've already factored out these huge numbers with respect to gamma. Okay, so now we're going to quickly discuss the two different problems that we're going to look at. They're both different types of problems related to the minimization problem number 5 here. So the first one is that we say the risk factor is the maximum value between phi I and xi. So for two vectors, you subtract the two vectors and you take the maximum value. Additionally, we set c, which was the extra c transpose x here, to 1. So you're trying to minimize with respect to x and z the maximum of xi I minus xi. So two things. One, since we're looking at a maximum, but we want to be able to minimize this function, and the maximum itself is not a nice function to minimize, we approximate the max with a smoothed log sum max, which is basically just an approximation for max with an extra factor of delta in front. So instead of max, we're going to have delta max, which is the approximation, and then we apply the scaling parameters of x bar and z bar with respect to gamma, and you finally end up with this optimization problem here. The second problem we're going to look at, which is a easier or a more robust problem, is the salvage fund problem. So the salvage fund problem takes in a lot more variables. So we first have, instead of xi, we're going to use L. So L is our losses. They're going to be drawn from a regular varying distribution as before, and they're going to Q be a deterministic matrix. And so instead of phi of xi just being a simple max function, now phi of xl is a linear programming problem such that the maximum funding occurs. So if you suppose x are people with or certain like firms or entities in a market, this problem finds the minimum funding required for a salvage fund such that no bankruptcy occurs for any of the firms with very high probability. So now that you have this risk factor, you can do your original problem and say you want to minimize the funding that you spend such that no bankruptcy occurs, and it's formulated as below. So in the last expression, we basically replaced phi with the actual thing of the delta max, the smoothed max. Here, phi is a linear programming problem, and we need to actually solve the linear programming problem, so we leave it in here. Okay. So how do we solve this problem? So we're first going to look at the maximization problem. So we have the delta max again. you can easily actually calculate the gradients of the problem with respect to x and z, as I did here. These are just applications of chain rules, which you, like, if you were to stare at them long enough, you could do. And in this case, g of xz is the function that we're minimizing. So here we have these two gradients, and now that you have two gradients and you're trying to minimize a function, you can use gradient descent, where you follow the two gradients down. So if you have a gradient in a certain direction, you move your x and z in the opposite direction. And what that'll do is you're going to eventually, since the c bar is a convex function, you're going to converge to the optimal minimum of x and z for this function. So now there's three major things. First, if we say for a one-dimensional case, we can actually show that the optimal solution is bar of x and 0 for x and z. And the naive SGD, if you were to supply SGD with these two gradients, it will converge. But the problem is it's very slow for the same reasons of the scaling before. So we need to develop a method that makes this path, this divergence of the gradients much faster than before. So I'm going to show a plot. So in this plot, I have different values of alpha. So alpha going to 1 is equivalent to gamma going to 0. And I'm basically running an SGD with these gradients. So I'm starting at two random values of x and z, and I'm seeing, and I'm running them for a large number of iterations, and drawing random values of psi and moving the gradients in the direction that's expected. And I'm seeing, hey, like what are happening to gradients? Are they converging or are they not? And in a naive method where you just apply these two gradients and you do the gradient descent, especially if you can see for alpha is equal to 0.9999, it's the convergence is absolutely terrible. You can barely, it doesn't converge to the right value. It's jumping all over the place. And the reason is in this expected value, both here and here, you're looking at the expected value of the max of the function being greater than z, as here, over gamma. So, and you have these, when gamma is really small, the gamma to the 1 over a and the over gamma become extremely big. And what happens is that it's very hard when you draw these samples of xi normally, such that this identity here and this identity here are satisfied. And what that means is that almost every single sample that you're going to draw, you're going to get zeros for these expected values. But in the cases where you do draw samples such that these identities are solved, you'd have massive gradients, and you want these massive gradients to occur because those are those rare event risks that you need to take into account. But you're not going to be with a normal drawing from say heavy distribution, in our case a Pareto distribution. So we need to sample psi in a way such that this can be calculated in a more mathematical term with bounded relative error as gamma goes to 0. And so this can be done with something called importance sampling. So we said that xi was drawn from a Pareto distribution with a certain scaling or a shape parameter. And we said that you can't draw psi in a normal way because most of them come to 0. So what we do is we draw psi in a way from a different distribution. We were originally drawing from the Pareto distribution. Now we're going to draw from a different distribution. And this formula here says that if xi is drawn from an original distribution, say a Pareto distribution, but you draw them from another distribution, you can actually just still calculate the expected value of psi of f of x or f of xi using this formula right here. And so if we find a good distribution, q of x, this alternative distribution that we're drawing from, we can calculate this expected value in a way that probably leads to a reduction in the variance, because our original distribution, our variance is going to be very high since we're drawing so many zeros with respect to this identity. So we can if we can find a proper q of x, then we can create a distribution and use importance sampling such that this expected value is easier to find. Now there's quite a bit of math going on in the back, but I can just say that you can find such a distribution such that this is bounded with error. And so if I include such importance sampling and then I calculate the expected value using this importance sampling, run the same SGD, voila. Here we have the same maximization problem with importance sampling. And so you can see that they're so much cleaner in terms of their convergence. It becomes much easier for each value of alpha to converge to its expected minimum. There's no jumping around, and it's showing that like these samples that we're drawing are not dead samples. They're actually useful for the expected value, and they're going down correctly to the minimum. So that's a really good sign. There's two things to note in comparison to the previous one. So in here, alpha, when alpha was 0.99999, it required almost 300 iterations of the SGD, and it didn't even converge. And it's like as alpha goes to 1, more and more iterations are required. In the importance sampling method that we make, as alpha goes to 1, the number of iterations does not seem to change a lot. It's in almost every single case, there's 30 to 40 iterations required. And finally, we talked about the smoothness already, so we have a good sign in terms of this maximization importance sampling method. So for the salvage fund problem, the less canonical example, a more applicable example, we can do the same thing with the gradients and applying an SGD. So we have these two gradients here, and you want to apply an SGD to go towards the minimum. There's two major differences. So first of all, we need to apply an importance sampling such that this is satisfied with bounded relative error. This is similar to the previous problem. So how do we apply importance sampling to do that? You can say, so phi is a linear programming problem, which means it's a minimization problem as well. So if you find one solution of phi, then you can say that the minimum problem if you can find one satisfiable x and z for x and xi for phi, then you can find that the minimum will always be less than that. And so basically, when you work through the linear programming, you can say that we need to introduce importance sampling such that this is satisfied here. The max of the random variables that you're drawing minus an m value is greater than or equal to the z bar over gamma to the 1 over alpha. And so you can do that. You can draw from another distribution such that this will be held with bounded relative error. Now, so we satisfied the importance sampling as before. There's one major thing. In the maximization problem, we had a soft maximization, and that meant that this derivative was actually easily calculable. In our case, this derivative is a bit harder to calculate. So we need to calculate this in order to use these gradients. And what you can do is you can estimate such a derivative of a linear programming problem with something called a subgradient. And the subgradient can be derived from the dual problem of the original linear program. So we had the original problem 5x epsilon, and here's the dual problem. It's quite long. You're trying to maximize with respect to two new variables, kappa and beta now, subject to all these constraints. And it can be shown that the subgradient of our original problem is the optimal solution to the dual problem. So if we can solve the dual problem, then we just take the kappa star, and that would be the subgradient with respect to x. If you wanted to take the subgradient with respect to L, you would use beta star, the optimal solution for beta. So if we can solve this dual problem optimization, it actually gives us expressions for the subgradients that we need in our original gradient of the entire minimization problem. Okay, so that's a good sign. So you can implement the same SGD. This time I had to add in extra factors of solving the linear program problem with a package called CVXPY using the SGD and the importance sampling I had to implement. And you can see here, I'll be a bit not as perfect as the maximization problem, that the same kind of type of convergence occurs in terms of the minimization problem value decreasing per iteration of SGD in an almost constant manner. It takes almost the same amount of time for different values of alpha, around 40 iterations, and it's very clean. There are still ups and downs in terms of this stochastic gradient descent, but it's not into the same level as, say, the original naive method was, where it's jumping all over the place in general, and it's going in a decreasing manner. And honestly, since it's a stochastic gradient descent, you expect ups and downs in terms of in terms of drawing bad samples. Okay, so now what we wanted to do is we wanted to run an experiment. So we have this importance sampling scaled method, and we wanted to run an experiment to see how efficient it was. And so what we did is we compared it to the naive non-importance sampling, non-scaled stochastic gradient descent method. So if I didn't apply the scalings of x is equal to x bar over gamma to the 1 array and such things, and I did not imply an importance sampling, how much worse would both the number of iterations required and the time per iterations be in comparison to this new method? So what we did is I ran for different values of delta or alpha. I ran this problem and let the salvage fund max problem run until convergence. And then I ran them both again. But now that I had these minimum values, I ran both of them, and I saw how much time does it take for the importance sampling scaled SGD method that we developed to converge to 5% of that minimum value, or to reach within 1.5 times the minimum value, and how much time does the naive method take. So if we see here in this table, the number of iterations required for the importance sampling is basically constant. It takes around 20 to 30 iterations for all of these values to reach 5% of the minimum value, while the naive one is almost exponential growth, 2, 156, 3,000, 22,000. So it requires an exponential growth for our original naive method, and our method is producing almost a constant number of iterations required. Secondly, the one other concern that you might have is, hey, does this extra importance sampling and scaling method take extra time? And so we recorded the time required per iteration of this method, and you can see that there's almost no increase in time. There's very slight differences, but basically the number of time required for both of these methods is exactly the same. And finally, there's one extra thing which isn't shown on this table. So when we get to alpha is equal to 10 to the negative 5, which are very small values, in order for such a naive SGD method to work, you need more and more samples per your the iterations that you're doing in your SGD. In order for them, so for instance, if I'm only drawing, say, 2,000 samples, and when you get to such low values, such low risk tolerance, then what happens is that almost every single sample that you draw is going to be 0. So you need more and more iterations, more and more samples in order for a naive method to even be possible of converging. Otherwise, everything will just be 0, and these gradients will never decrease or increase in the ways that you want them to. However, for the importance sampling method, we generate these samples in a way that has bounded relative error. And what that means is actually I didn't need to draw 15,000 samples for such low values of alpha in the importance sampling iterations. What actually happens is, for all of these, I'm very confident that I could use 2,000 or so samples per iteration, and the importance sampling would still converge, which is not true of the naive method. So, in conclusion, we aim to optimize a convex chance-constrained optimization function, the conditional value risk function, as an approximation of our original risk-constrained problem. We applied two major methods, a scaling argument for the heavy tail distribution and an importance sampling method in order to reformulate the algorithm and the solving the problem. we saw that when we applied such importance sampling methods, the convergence of the solution is much faster in terms of both the runtime, the number of iterations, the number of samples needed, and the time per iteration. So these experiments show much more improvement in this method over a naive SGD method, which you may initially think to use to solve. So there's a lot of future experiments to test different hypotheses of efficiency in terms of our new method. So for instance, we could see from this table that there's approximately constant growth in terms of the iterations required for the importance sampling versus what we see is almost exponential growth for the naive method. So creating a bound on this naive method would be one good future bit of work that we can do. Additionally, what we applied was a scaling plus importance sampling method to the problem. One thing to do is look at what is the efficiency of just scaling, just applying the scaling parameters, or just applying importance sampling. Is one more important than the other? What would happen if we only applied one? Would it still be constant time? And these would give us like more insight onto which one is providing the main main efficiencies in terms of this method that we're using. And finally, we can see, hey, what if we set certain initial conditions for both methods differently than what we had before? Would that make a lot of difference in terms of the number of iterations that are required? Because if you start a bad initial conditions, it could take a lot of time to get out of these initial conditions, especially for the naive method. So to see, hey, what is happening with these initial conditions? Are they the reason? Could they possibly be the reason for this? The immediate answer would be what you would think is no, but just to show that is the case. Finally, I'd like to thank my professors, Dr. Jose Blanchett and Dr. Bert Smart, for helping me through the project, and I'd like to thank Fan Zhang, a PhD student under Jose Blanchett, for helping me through this entire project. Thank you.